All right. So we'll get started here. So is there a particular, I honestly don't think there, I don't know, it's hard for me to, it's hard for me, guys. Everything in here seems easy to me because I know trigonometry. It's hard for me to unknow it, you know. Let's see here if I can work a problem for you guys. I think this, some of these symbolic inverse, let's just work some examples here. What's the tangent of the inverse sine of x minus 1? Uh-oh. Oh, it's that. Whenever beeps like that, I think it's the camera, but of course it's not. All right, so this is one of your, I don't know, actually I don't remember if I assigned this or not, but it's like, it's a reasonable problem. This is number 37 from, I can't remember where it's from. I think it's a section on inverse. 6.3. 6.3 is where it is? 6.3. Yeah, this is from 6.3. So how do you, so the goal here is to find an algebraic expression that, that is this. So the question is, what is that, right? So the approach I take to problems like this is just to say, okay, so inverse sine of this is some angle, right? So let's let inverse sine of x minus 1 equal to theta, right? So I'm just giving a name to the angle that we're trying to analyze, because that's going to be a useful crutch for us to kind of work through it. Now, if that's the case, then remember how does inverse sine and sine work, right? Remember, if we take sine of both sides, what happens? What's the sine of the inverse sine? These are inverse functions, right? So this just gives me back x minus 1, right? Equals to sine theta. Now, we're trying to calculate, our goal here is to calculate tangent theta, right? Like that's the whole problem. That's the question, all right? So with this, our goal, calculate tangent theta. So do you guys have any ideas? Like, now that we have this in front of us, sine theta is x minus 1, what should we do to try to get our paws on tangent theta? What should we draw? We should draw a triangle, right? We should draw a triangle that relates to this expression. So a right triangle, right? So let's try that out. And you guys tell me. There's not a unique choice here. Like you got different things you could do. But if sine theta is x minus 1, and sine theta is also what? The opposite over the adjacent. The opposite over the hypotenuse, right? Opposite over hypotenuse is sine, right? So what should I put there? Like what would be reasonable choices for the opposite side and the hypotenuse? You're like, well, it's not a fraction, it's x minus 1, right? How can you see x minus 1 as a fraction? How about this? If you allow me this short manga-style calculation. X minus 1 divided by 1. There you go. Now it's a fraction. So what does that suggest? That suggests we make the triangle have a hypotenuse of length what? So we put 1 on the hypotenuse, right? And we make the opposite side x minus 1. Then how should we proceed? Like to figure out, well, the tangent is the what? The opposite over the adjacent. Now we don't even know the adjacent yet, right? Let's give it a name. Let's call it y. Right? We don't know what y is. However, what do we know? This is a right triangle. So how are y, x minus 1, and 1 related? The what? Well, the same. What theorem do we have to relate the hypotenuse and the sides of a right triangle? The Pythagorean theorem, right? So, excuse me, I have this very much not delicious candy, but it helps. So, we know the Pythagorean theorem, which says what? It says y squared, right? Right, plus x minus 1 squared equals 1. Now, we need to find y, right? Because, like, tangent theta is going to be what? Tangent theta is going to be x minus 1 over y, right? Opposite over adjacent. So we're almost there. So we can solve for y, right? Y squared is 1 minus x minus 1 squared. Of course, we can do a little bit better than that. We can square that out, right? That's 1 minus parentheses x squared minus 2x plus 1, right? The 1's cancel, and we have 2x minus x squared, right, for y squared. So what does that tell us? That tells us that y is the square root of 2x minus x squared. All right? And then let's put it all together. Therefore what? Tangent theta is, again, opposite over adjacent, right? Which in this case is x minus 1 over y. So therefore, tangent theta is equal to x minus 1 over the square root of 2x minus x squared. And finally, returning back to the original problem, the tangent of the inverse sine of x minus 1 is thus equal to x minus 1 over the square root of 2x minus x squared. So I thought, what's that? Radical in the denominator? I think so. I mean, is there a problem with having a radical in the denominator? I don't suppose so. I mean, as with anything in the denominator, you can worry about it being 0, right? But I think here, if I factor that, if I look at this, I'm looking at x minus 1, the square root of, x times 2 minus x So then you can ask the question, given the context here, is it possible for that to be 0? I don't know. I mean, well, I don't really, I'm kind of at a loss of how to say more about that. I mean, it is, for what it's worth, that is the answer in the you know, answer to the question according to the textbook, if that matters. It matters to me. I'm a little bit low on my energy, so like it's encouraging to me when I find the answer in the back of the book. I mean, it's comforting to me to have independent corroboration of my answers at the moment because I'm a little bit low energy, you know. Any questions? Like, so seeing that one, do you think you could do similar ones there? We can work let's work another one, right? Let's work another one of these. Oh. So this kind of calculation comes up later in calculus when you're working on inverse trig functions. A lot of times you want to make these kind of triangles to help understand like how to find it. There's often an algebraic formula that relates to these inverse trig functions, and this is often how we come to terms with them. So here's another one, cosine of inverse sine of 1 over x. So the question is to basically we're trying to find an algebraic expression for this in terms of x, all right? Okay, so it's going to be the same game plan again. We're going to call we're going to call this right here theta. Theta be equal to the inverse sine of 1 over x. So then that means what? Sine theta is what? Right, sine theta is equal to the sine of the inverse sine of 1 over x, which by inverse function, by the definition of inverse sine is 1 over x, right? Just like you said. And again, we're going to want to find a triangle, right? So let's think about it. What kind of triangle? What triangle? This one's a fraction, so it's kind of easier in some sense, right? We can think about this as being opposite over hypotenuse, right? That's sine. So let me draw a triangle here. You guys tell me what should I make the sides? Opposite is 1. Hypotenuse is x. And it's kind of a quirk of the examples I've picked. Both times the adjacent side has been the unknown side. But that's just, it doesn't have to be that way, obviously, right? It's just because we worked inverse sine problems, I suppose.
Will it be like where it says
Where, there could be one where like the hypotenuse is the unknown and you have a fix on the other two. I'll try to, maybe we can find a problem like that next. So we have this, then we do what? Pythagorean Theorem. So 1 plus y squared equals to x squared. The algebra is a little bit easier here. Y squared is equal to x squared minus 1. So therefore y is the square root of x squared minus 1, right? Now our whole goal was the whole question was what? We were trying to calculate what is the cosine of the inverse sine of 1 over x, right? But that is the cosine of theta, given our definition of theta. And by the triangle above, and the fact that we just figured out what y is, cosine theta is equal to what? Well, I'll write it down symbolically again. It's the adjacent over the hypotenuse, right? Which in this context is what? Yeah, square root of x squared minus 1 over x. And there you go. That's a wrap. That is the algebraic expression which is equal to the cosine of that inverse sine. Now, of course, we can go and we can spend some time on, numerical inverse sine problems here next. But I thought I should actually work a couple of these because I think it's a little bit I feel like this is a little bit removed from the things I've showed you in the video already about inverse sine, right? Like this is kind of a next step problem. But I think these are actually really, really healthy, and these will help you build your algebra skill. Now, so any questions about the homework again? Okay. Let's see here. I think this is number 27. I'm kind of going back actually at this point, and working some problems here. Number 27. So we're supposed to figure out the inverse tangent of the sine of pi over 3. Now, of course, one way you could do this is what? You could get your calculator out, and you could just work it out, right? But I'll show you how to think through it in terms of exact expressions. So, if we call this thing inverse tangent of sine of pi over 3, whatever that is, this is equal to some angle theta, right? And so, taking the tangent of both sides, what happens? And again, as a student, I almost feel kind of silly showing you this because, I mean, goodness gracious, guys, I would just use if I was in your position, I would just use my calculator to work this out. I mean, to be totally honest. But I want to show you how you can work through it, steps, without a calculator, because this is a standard special angle, right? Now, of course, this gives us what? This gives us sine of pi over 3 equal to the tangent of theta. Now, what is the sine of pi over 3? I'm sorry. What I'm doing right now, it offends me. I have to stop. It's just dumb. It's just dumb. Let's try this again. How about this? We're trying to figure out what's the inverse tangent of the sine of pi over 3, right? So what is that? That's inverse tangent. What's sine of pi over 3? Let's not complicate this. Sine of pi over 3, square root 3 over 2, right? So then what? Then you put it in your calculator is what happens, okay? So then you plug that in your calculator. What you get is 0.7137 radians. So there are other problems where you can actually you don't need to use the calculator, but this is not one of them. So maybe this problem's, I'll go over here. So I'm sorry, I was working these out, and sometimes you find a way to make a problem more complicated than it actually is, and that's what I was doing at the start there, right? Okay, so let's work another problem here. Hopefully this one will be more interesting. is number 31. All right, we're supposed to find the inverse tangent of the sine of minus 5 pi over 2. All right, so let's think about this one. We're looking at inverse tangent of the sine of minus 5 pi over 2. Okay. Now, let's see here. So the question is, can you guys tell me what is the sine of minus 5 pi over 2? What is it? What are different ways you could figure that out? Well, one way you could figure that out would be to use a calculator, right? Another way you could just draw the graph of sine, right? What's the sine look like? Remember? So this is pi over 2, right? This is minus pi over 2. This minus 3 pi over 2. This is minus 5 pi over 2. So the sine of minus 5 pi over 2 is equal to minus 1. So we're looking at inverse tangent of minus 1. Now there are some inverse things you should know about, right? What are some things you should know about inverse trig functions that you should know without, like, maybe you should really be able to do these even without, like, relying on a calculator, right? Let me show you some examples of those. This is one of them, actually. So, well, let's see here. Inverse tangent is an odd function, isn't it? So this is also minus the inverse tangent of 1, right? So let's think about this. If you have theta equals to inverse tangent of 1, what does that mean? That means the tangent of theta is equal to 1, right? Tangent of theta equals to 1. What does that mean? What is tangent? Tangent is opposite over adjacent. So what kind of triangle has opposite over adjacent equal to 1? Do you guys, it's a 45, exactly, it is a pi over 4, right? Pi over 4. It's that kind of triangle. So what does that tell us? That tells us that the inverse tangent of 1 is pi over 4. See? This is equal to minus pi over 4. So my point is, that I think you can work out without a calculator. I realize that there's kind of a tension in here, right? Because you have a calculator to use, but I really want you to, there are certain things that I want you to know leaving this course, right? One of those is that the inverse tangent of 1 is pi over 4. What are other really important inverse trig basic facts that we should know? Let's just kind of go through a little list here. And I'm going to start out with what we know from sine and cosine. For example, sine of 0 equals to 0, right? Cosine of 0, what is cosine of 0 equal to? 1, right? So if you take the inverse sine of that expression, that tells us what? That tells us inverse sine tells us that, inverse sine of 0 is equal to 0. So the inverse sine of 0 is 0. If I just take the inverse sine of this expression, right? Because inverse sine of 0 is 0. And likewise, cosine inverse of 0 is equal to 1. Right? So what's the inverse tangent of 0? What's tangent of 0? Yeah, tangent of 0 is 0, right? Because tangent of 0 is sine of 0 over cosine of 0, which is 0 over 1, which is, of course, 0, which tells me that inverse tangent of 0 is also equal to 0. All right? So, all right, let's just kind of like summarize what's going on here. The big idea is that the inverse sine, inverse cosine, inverse tangent, they are inverse functions to sine, cosine, and tangent, right? Now, we have to beware that they're local inverses, right? So they're never going to give us back angles that are, we know the range of the inverse trig functions. We'll talk more about that here. Let's look at number 55 here. Work another homework problem for you guys. Actually, you guys good on all this? Can I erase? All right, here's kind of I'd like to work more problems like this. I'm going to try to, it is on my list of things. Hello? Oh, I have to call you back. I'm in the middle of something. Sorry about that. It's a 205 number is why I picked it up, but no idea who that was. Well, it's probably somebody from church, but I don't know. I don't know who it is. Oh, goodness. Sorry about that, guys. Eventually, I'll learn how to silence my phone. All right, so we're told that we've got this isosceles triangle. What does isosceles triangle mean? Yeah, two sides are congruent, right? And we're told that they have length 9, right? And we're told that the base down here has length 8, all right? And then the question is, theta is what? That's the whole problem. All right? So this kind of problem we can make quick work of with the inverse trig functions, right? Now, the problem with this one is we don't have a right triangle to start with, right? So you got to use some kind of geometric intuition here to get going. And so here's what I would do. I go, okay, well, this is 9, right? And then I just, draw this like that, right? And that gives me a right triangle here. And so if you look at this, right? What's the length down here? Right? It's an isosceles, right? So the symmetry here says that this distance and this distance got to be the same, right? So it has to be 4, right? Now that's the theta we're looking for. Exactly. So we can use cosine. Cosine of theta is what? 4 over 9. And obviously this is not a special angle or anything like that, but we can use our handy dandy calculator. Take the inverse cosine of both sides. What do we got? inverse cosine of cosine theta is inverse cosine of 4/9. So that tells me theta is the inverse cosine of 4/9. And we can figure whatever that is out using our calculator, right?
1.11.
Yeah, 1.11 radians. And of course, if you wanted degrees, you could switch your calculator over to degree mode, or we could just convert, right? Maybe that's a good exercise for us. How many degrees is that? .11 radians times what? 180 degrees over pi radians. So what's that give us? Yeah. I got 63.6 degrees. Is that what you got? No? So 1.11 times 180 divided by pi. I mean, basically 180 over pi is kind of like 60-ish. And then, so yeah, 63. And I think, by the way, that, like, I don't know, personally, when somebody says, whoa, I want you to make a roof with a slope of, I mean, with an angle of like 1.11 radians, I'd be like, huh? And if somebody told me, well, I want you to make a roof that has like a, 63.6 degree tilt, then I'd be like, oh, okay, I kind of know what you're talking about, right? Like, I mean, radians are beautiful and wonderful for mathematics, but degrees are great for actual physical geometric questions and physics. Of course, physics. All right, so that's, I think, a good sample of these kind of problems. Is there another homework problem that has been troubling you I can work? No. All right, well, let's start talking about how to solve trigonometric identities, all right? So verifying trigonometric identities, how do we do that? Like, how's that work? How do we show our work on that sort of thing, right? At the moment, we really don't have too many tools at our disposal. So as we think about trigonometric identities, I think the main ones I think about at the moment for you guys are that cosine squared theta plus sine squared theta is 1, right? If we take that and we divide by cosine squared, what do we get? So this gives me 1, and that gives me, this gives me sine theta over cosine theta squared, right? 1 over cosine theta squared. What is this, though? What is sine theta over cosine theta? Remember, sine theta over cosine theta is tangent. So this gives us 1 plus the tangent squared of theta equals to, this is secant squared, right? So this is the tangent secant identity, and of course this is the sine cosine identity. What's another one you might want to work out? What happens if instead of dividing by cosine, we divide by sine squared? What identity does that, what identity does that give us? So we have cosine theta, cosine squared theta. I'll divide by sine squared theta. Okay, so what are we looking at here? We've got cosine theta over sine theta squared, right? Plus what? Plus 1. 1 over sine theta squared, right? What is this? What's cosine over sine called? Well, this is the so-called cotangent of theta, right? So this gives us cotangent theta, cotangent squared theta, plus 1. Now 1 over sine is called the cosecant, so this is cosecant squared theta. So there you go. These are the three sort of like fundamental, I would call them Pythagorean identities, that relate sine, cosine, the secant, and the cotangent. All right. So whenever we're working with like identities, we always need to have these tools in our toolkit. All right. We try to find us a.
We're going to have to start making them as equal, where you'll give us like cotangent equals cosine.
Well, yeah, I'll try to. I'm going to. Exactly. The question is, all right. So what are the problems, right? That's your question, right? What's the problem? And so let's just start going down the list here and working a few. I'll start out with a real easy one. It's number 5. And we're just supposed to, it says simplify the expression, all right? Simplify. And here's the expression. Sine x times the cosine x times the secant x. Okay, so like how do we do this? What is there to do? Right? What is there to do? So really the only thing to do here, and I think as a point of like, whenever somebody says simplify something, it just begs all kinds of questions, right? I mean, what's the simplest solution? Look at today's politics, right? There's obviously disagreement as to what's the simple solution, you know? People don't agree on what's simple. But in math, I think as a sort of a point of, you know, aesthetics, like we'd like to make things in terms of sine and cosine if we can, probably. So we want to keep the sine and the cosine, maybe. But what's secant? It's what? It's 1 over cosine, right? So this is 1 over cosine. Okay, so great, they cancel. And what do we got? We've got sine x. There you go. See, it doesn't have to be hard, right? Yeah. Let's look at number 8. Here they ask us to simplify cosecant x. All right, plus cosine x times the cotangent of minus x. Ooh. Very, very, very daunting. They put a minus in there. Think about this. cotangent is what? It's what? It's 1 over tangent. That's true. I'm going to go a slightly different direction, though. So this would be cosine of minus x over the sine of minus x, right? Because cotangent, cosine over, I mean, you're right, it's 1 over tangent. That would also be fine. Yeah, well, I just want to point out, cosine is what? Cosine is even. Sine is odd, right? So cosine eats the minus, and the minus comes out of the sine. All of this to show you this is minus cotangent of x, all right? So that's my first comment to you, is that we can replace cotangent of minus x with minus cotangent x, all right? So we have cosecant x minus cosine of x times the cotangent of x. Let me say by star. Now what can I do? How about this? Convert everything to sine and cosine, see what happens. Right? Convert everything to sine and cosine. What's cosecant in terms of sine and cosine? 1 over sine. And how about cotangent? Cosine over sine? Right. Well, now this is getting kind of interesting. I mean, so beauty's in the eye of the beholder. Some people would say, well, it's simplified now, because you got in terms of sine and cosine. I think that that's a little bit of a stretch. I think we can do better. I'm going to erase my poorly planned comment below the calculation. Sorry about that.
Would it be 1 over sine minus 2 cosine over sine x cosine?
1 over, let's see here. I guess my question is, could you rewrite this as a fraction? Is there a common denominator to see there? I don't think there's a 2 there. It'd be a square. But so look, there's a denominator of sine x. See that? We can put sine x here. Right? And then we have 1 here. Cosine times cosine minus cosine squared x. But remember our fundamental identity. Sine squared plus cosine squared is 1, right? You got to also think about, if sine squared plus cosine squared is 1, what does that say? Sine squared plus cosine squared. That says that 1 minus cosine squared x is what? It is sine squared x. Right? So we can trade 1 minus cosine squared x for sine squared. See, this is equal to sine squared x over sine x. So what actually do we have here? We have sine squared over sine, which is just sine. Now that does that look like sine to you? No. Right? That's kind of a neat example, actually. Right? So, I mean, you're like, well, this is sort of like the mathematical analog of being asked to clean up a messy room, right? Like somebody's giving you this pile, this heaping dumpster fire of a stupid way of writing something, but it's our job to like unravel it and try to come back to something simple. That's what this particular section's about. And what it's going to do, what the section's going to do, it is going to inculcate the basic identities about sine and cosine, cotangent, cosecant until we're really good at them. So we'll do more of these next time. We're just getting started here, and then eventually we'll be moving on to more interesting things like the adding angles identities. That's where my heart is. Like that's really, really cool stuff. And but anyway, I think it's a good place to stop. So thank you for bearing with my low energy.